the way that would work would be, we would going to use ideal gas law. So PV equals nRT again. So let's think about this. What are the units on your molar mass? You have molar mass. Grams per mole, right? Molar mass is the grams per mole. So that's what we got to find. We want to find the grams per the mole. So the problem says a sample of gas has a mass of 2.44 grams. So there's the grams. Its volume is 0.310 liters. Its temperature is 65 degrees, and its pressure is 925 millimeters of mercury. What is the grams per mole? What is the molar mass? So we already have the grams. See that? There's the grams right there. So what we need to find is the moles part. So we have already, we can see we have volume, we have temperature, and we have pressure. So we can just rearrange and solve for, the moles, N, right? So let's do that. So N is going to be PV over RT. But we know from R, liters, atmospheres, moles, and Kelvin. So which of those units do I have to convert first before I can plug them in there? Pressure. Okay, pressure is in millimeters of mercury, so let's convert that one. So pressure is 924 millimeters of mercury. And we know that 1 ATM is exactly 760 millimeters of mercury. So grab our calculator, see, already punching away there. Somebody can tell me, what is that in atmosphere, somebody? What? Anybody? 1 point what? 1.22. So anybody else? Okay, that's the pressure. What else do we have to convert? What else is not in liters or atmospheres or moles or Kelvin yet? Temperature, yes, is in Celsius. So we'll take 65 and add 273. And we'll get 338. Okay, so let's punch that in here now. So P, 1.22 atmospheres. V, 0.310 liters. R, 0.08206 liters, atmospheres, per mole, Kelvin. And our T, 338 Kelvin. Okay, let's make sure units are canceling. We're left with the right thing. So atmospheres, atmospheres, liters, liters, Kelvin, Kelvin. Good, we're left with moles, which is what we want. Oops. So how many moles did we get? Anybody?
0.014.
Yeah.
How many sig figs should we have?
3.
I'm going to say 3, so 0.0 what? 136. Okay, so that's the moles. So we're almost there. But we want the what? The molar mass. We have to take the grams per mole. Take the grams and divide them by the moles. So I'm running out of room here. So let me erase them here. So let's take the grams divided by those moles we just found. So let's see, what's the molar mass now? So our mystery gas, we can help to narrow it down once we know what the mass is. What'd you get? 17.9. Okay, so it's around 18. So I don't know. Maybe it's water. H2O is about 18. Maybe it's methane. CH4 is about 18. Something that's about 18, right? So it kind of helps to narrow down the possibilities there when you know the molar mass. Okay, well, let's try one more of those and then we'll move on. So your turn. What's the molar mass if the sample weighs 792 milligrams, has a volume of 0.295 liters, a temperature of 85 Celsius, and a pressure of 783 millimeters of mercury? So your turn. Try it out. Help each other out if you need to. Go through and label what you know. What's P, what's V, what's T, what's N, or which one's missing. Help each other out. Compare, contrast, see what you're doing, see what they're doing. See if you're on the same track. Talk it over. Feel free to talk.
Wait.
0.0103 more. Try it again. Do that, or no, wait. No. Why do you have, why?
I have 353. That's here.
That's too quiet. Your math is right. Your math is right. You just put it later on.
Okay, so I see some 76 point somethings, and is that what you're getting, most of you?
Yeah.
Okay. Well, let's work it out real quick. See if we can get that too. So we have, it looks like we have the mass right here. What else we got? We have the volume, we have the temperature, we have the pressure. So we can find the one that's missing, which is the moles in. So same thing, we'll take Pivner, the pervert, and solve for N. N equals PV over RT. So, which of those do we have to convert? Temperature and pressure. Temperature, we're going to take temperature, 85, we're going to add 273. So it's at 358. Pressure, we'll take 783 millimeters mercury. Turn that into atmospheres. What's that give us here? 1.03 atmospheres. Okay. So P 1.03 atmospheres. V 0.295 liters. R 0.08206. Let's write all these units in here. Liter atmosphere over mole times Kelvin. T 358 Kelvin. So make sure everything cancels. Let's look here. Atmospheres, atmospheres, liters, liters, Kelvin, Kelvin. There we go. We're left with moles. So, how many moles did you get? I'm sorry? 0.0103. Okay, so we want grams per mole. So we've got to do one more conversion. What do we got to do? Turn those milligrams into grams. Yeah, so let's turn 792 milligrams into grams. So 1 milligram, 10 to the negative third grams, so 0.792 grams. So the molar mass, let's put MM, molar mass is going to be 0.792 grams over 0.0103 moles. And what was it? What'd you get? 76.9. Awesome. Okay. Fun with gases. All kinds of fun stuff. Any questions on that? Okay. We're rolling along here. Okay, now, so let's tie it together here back with reactions now and stoichiometry. So, because you don't always react solids liquids, you can also react gases, of course. So, here's the reactor, the reaction. I think this is the one for like professional strength liquid plumber or something like that. It's one of those things. So, you know, so you take it and you pour it down your toilet or whatever, and it breaks up the clogs. Well, how does it do that? Well, typically what it is, it has really strong sodium hydroxide and aluminum powder. And then when you dump it into water in the toilet, it begins to react. And it makes this stuff, but it also makes lots of hydrogen gas, begins to bubble and bubble and bubble. And it's also exothermic. It gets really hot. So you have two things going on. So you get the really hot stuff, begins to melt any grease or oil that's clogged up in your toilet or your sink. And then all the bubbles and the fizzing and stuff kind of like jostle it loose and break it up and make it go on down. So, in this case it says, what volume of hydrogen gas are we making at 23 Celsius and 1 atmosphere if we used 3.12 grams of aluminum and an excess of this. Okay, so let's break down what this question is asking, because it's a little confusing. So let's write down what we know. So what do we know? It says, what volume of this? So my question is, how many liters of that? That's what I'm trying to find, right? What do I know? I know the temperature of that gas. I know the pressure of the gas. I want to find the volume of the gas. Pressure, volume, and temperature. So which other one am I still missing? I'm missing the moles of the gas, right? Well, they told me I have 3.12 grams of aluminum. How could I use that to help me find moles of hydrogen?
Theoretically, or like something like that.
Something like that. So how would I do that? How would I turn mass of aluminum into moles of hydrogen? So I would turn mass of aluminum into moles of aluminum, and then mole to mole ratio. For every 2 moles of aluminum, I'm going to make what? 3 moles of hydrogen. So that'll be my moles. Then I'll have my N, my T, and my P. I can find my V. So we can predict, okay, how much hydrogen gas will come bubbling out of your toilet. So let's do this. So I'm going to go to my next slide here. You get that written down. Well, actually, you don't have to write it down. It's also on here. I wrote it up here again. Okay, so let's see. First we're going to take the mass of the aluminum, and we're going to turn it into, we want to find N, moles of hydrogen. So, what do I do first? Molar mass. So find aluminum on your periodic table. 26.98 grams is a mole of aluminum. And you're right, Hilda, you said mass mole to mole ratio. So how do I relate aluminum to hydrogen? Tell me again. For every 2 moles of aluminum, it's 3 moles of hydrogen. Okay, good. So let's figure that up here. 3.12 divided by 26.98 times 3 divided by 2. 0.173 moles. Is that what you got? Okay, so now we have N, we have P, we have T. So now we can solve for V. So PV equals nRT, V equals nRT over P, right? So we just found our moles. It was 0.173 moles. R is always 0.08206 liter atmospheres per mole Kelvin. What's our T? Yeah, 23 Celsius plus 273 then, so 296 Kelvin, thank you. Over our pressure. Pressure was given as 1 atmosphere. So yes, that's about the standard atmosphere in your bathroom probably, around 1 ATM. So, how much gas will come bubbling out from only 3 grams of aluminum, which is 3 grams is not much, right? So 3 little grams of aluminum produces a surprisingly large volume of hydrogen gas. How much?
4.21.
4.21. Anybody else? So people are going, huh? Anybody else get that? Anything different? Didn't bother to try? Okay.
You're right, it's like 4.202.
4.2.
4.2. Yeah, 4.20, yeah. So yeah, so think about that for a second. 3 grams, from the lab, right? 3 grams is like hardly anything, but you get over 2 full 2 liters of gas out of 3 little grams of aluminum. So it makes a much bigger volume of gas. So all that's bubbling like that in the toilet, breaks up all the clogs and stuff for you.
I
with
ended up
heat.
4.21 because I didn't round the moles.
Okay.
I saved it until very
Yeah, doesn't matter, right? Because sig figs, the last one's uncertain anyway. 4.2, 4.21, 4.22. Good enough. Okay. So, here's another one, might be important. Oxidation of glucose in your body. Okay? So in your body, when you metabolize glucose, it reacts with oxygen when you breathe it in, metabolizes it, produces carbon dioxide and water. What volume of carbon dioxide would be produced at body temperature, which is about 37 Celsius, and 0.970 atmospheres, when 24.5 grams of glucose is consumed? So let's write what we know here again here. So we know 24.5 grams of this. That was messy. And our goal was to find liters of this. So volume is what I want to know. Here's my temperature. Here's my pressure. So I have the volume of carbon dioxide. I'm sorry, I don't have volume. I want the volume of carbon dioxide. I had the temperature of carbon dioxide. I have the pressure of carbon dioxide. I don't have the what? The moles of carbon dioxide. So same thing. Taking mass of glucose, turn that into moles of carbon dioxide. So do that first. I can just plug it all into your ideal gas law. And how much carbon dioxide would you exhale when you burn 24.5 grams of glucose? Oops, go back. So we're going to do the similar thing. We're going to turn mass of glucose into moles of glucose into moles of carbon dioxide, and that'll be our N. So 24, try a little smaller pen, 24.5 grams of glucose, C6H12O6, and molar mass of glucose, 180.18. Okay. Okay, how do I relate that to carbon dioxide? Well, yeah, which is what is it? What's the ratio? 1 glucose to 6 carbon dioxides, right? 1 mole glucose. 6 moles carbon dioxide. So what's that give you? 0.816? Awesome.
No, it's like already this time.
Okay, so we want to find volume of carbon dioxide. So that's going to be, what, nRT over P? So N, we just found 0.816 moles. R, 0.08206 liter atmosphere per mole Kelvin. T, 37 plus 273, what's that? 310. And then pressure, a little bit less atmospheric pressure. Maybe there's a low pressure cell coming through. 0.970 atmospheres. Check our units, make sure they cancel out. Moles, moles. What we got? Atmospheres, Kelvin. Okay, and how many liters did you say? 21.4. Again, that to me at least is a surprisingly large number. That, right? 21.4 liters, that's 10 and a half, 2 liters. And all you burned was 34 grams of glucose. I'm sorry, not 34, 24 grams of glucose, not much. You got 10 and a half, 2 liters. Carbon dioxide, right? That one, right? That's a lot of 2 liters you breathe out. Just not a little bit, so. Okay. How about this one? What volume of oxygen now would you need at 1 atmosphere and 298 Kelvin to completely oxidize or completely metabolize, react with 50.0 grams of glucose? So similar kind of deal. 50 grams of glucose, what volume of oxygen? So just kind of keep in mind here, we have the temperature of the oxygen. We have the pressure of the oxygen. What we don't have is the moles of the oxygen or the volume. But the moles we can get by turning the glucose into oxygen. Oops. So 50.0 grams, we can turn that into this. Okay, so same thing again, 50.0 grams of glucose. The molar mass you told me was 180.18 grams per mole of glucose. And once again, it is a 1 to 6 mole ratio. For every 1 glucose, you need 6 oxygens. 1 mole glucose, 6 moles oxygen. So how many moles of oxygen was that? Anybody?
1.67 moles.
1.67? Okay, then we're trying to find volume. So nRT over P. So 1.67 moles times R, 0.08206 liters, atmospheres per mole, Kelvin. T, 298 Kelvin. P was 1.00 atmospheres. So let's make sure everything's canceling like it should. Moles, moles, Kelvin, Kelvin, atmospheres, atmospheres. There you go. We're left with liters. And what'd you get? 70? I say 40.8? 40.8. Awesome. Okay. So we're tying it all together here. Okay. So we'll come back and do some more stoichiometry here in a second. First, we're going to mention yet another law. We've had Boyle, Charles, Gay-Lussac, Avogadro's, combined, ideal, and now another one named for an individual named Dalton. You might remember John Dalton. He was the guy we mentioned earlier on the semester with the atom. He came up with the atomic theory, and he's an English school teacher based out of Manchester, and remember he kind of went through and kind of postulated what he thought atoms would be, how they would behave and such. Well, he also worked with the gases. And his law is pretty simple. It basically says if you have a mixture of several gases, the total pressure of the mixture is just the sum of the pressure of each individual gas added together. So for example, air is a mixture of nitrogen, oxygen, carbon dioxide, things like that. So the total pressure of the air in this room is the pressure of the nitrogen in the room, plus the pressure of the oxygen in this room, plus the pressure of the carbon dioxide in this room, plus the little bits of helium and argon or whatever is floating around here. Okay, so pretty straightforward. You just add them all up, and that gives you the pressure. So the pressure of each individual gas is called the partial pressure. So out of the whole, the partial pressure of just the nitrogen, the part that's just the oxygen, the part that's just the carbon dioxide, the partial pressures, in other words. Okay. That's basically it. So you just add them all up. So you can see Oxygen, you know, not oxygen, air's total pressure, around 760 milliliters of mercury. Well, if you add up the nitrogen plus the oxygen plus everything else, that's where you get it, right? So you just add them all together. Just pretty straightforward. Just add them right up there. Okay, that was John Dalton, our buddy from Manchester, England. So just a real quick, easy one here. Let's say you have a sample of air you snag, and it has nitrogen, oxygen, and argon in it. If there's 587 millimeters per mercury of nitrogen, and 158 millimeters of mercury of oxygen, and 7 millimeters of mercury of argon, what's the total barometric pressure? No, not necessarily. Not necessarily. It didn't ask for an ATM, so we'll just leave it. So what would I do? Just add them all up. Pretty easy. So the total pressure is going to be the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon. So yes, we're just going to add them all up. 587 plus 158 plus 7. So what'd you get?
752.
752?
Yeah.
52 millimeters mercury. Yeah, that's pretty straightforward, right? Okay. Okay, let's do one example. So, let's say you're working in a hospital, have an anesthetic to give to a patient. It's a mixture of cyclopropane gas and oxygen gas. The total pressure of that mixture is 1.09 atmospheres. So, and the partial pressure of the cyclopropane is only 73 torr. So what's the partial pressure of the oxygen? So we get two gases, cyclopropane plus oxygen. Those are combining to give me a pressure of 1.09. So if the cyclopropane is 73, how much is the oxygen? So think about that, talk about that. Remember, 1 atmosphere is exactly 760 millimeters mercury, or torr, same thing. 1 atmosphere is 760 torr. So what's the pressure in torr of the oxygen?
What?
755 torr of oxygen? Okay, let's try it out real quick. So let's turn the atmospheres, the total atmospheres, into torr. So 1.09 atmospheres. 1 ATM is 760 torr. So 760. 828 torr. Okay, well that's the total, right? So to find the oxygen, I'm just going to subtract, right? Because we know the total is the pressure of the C3H6 plus the oxygen. Right, so we can just subtract the 73 here. This is the total. I'm going to subtract the C3H6, and that'll leave me, what'd you get, 755?
Mm-hmm.
755. So that's how much oxygen you would need to mix in there, so you don't have too much or too little of the anesthetic. Yes?
Is there a molecular reason why the O2 has such a higher pressure than the cyclopropane?
Why?
Or are there just numbers even?
Why it has a higher?
Why does it have a higher pressure? Like,
Because there's more of it, so there's more of it bouncing off the walls, creating more pressure.
Okay.
Yeah. The pressure is just how many of them are bouncing around, so there's just more of the oxygen. Yeah. Okay, oh, by the way, here's a fun little thing I saw also when I was in London. These are some letters between, remember our buddy Dalton and that other guy, Gay Lussac. So you can see they're writing back and forth in the 1600s talking about gases and atoms and things. I thought it was kind of interesting. So I found letters from Gay-Lussac to Dalton, and Dalton writing to Gay-Lussac. It's kind of neat, I thought. So there we go.
Such great handwriting.
I know. Oh, this is amazing. This is amazing. Ours sucks. Ours sucks. When we teach cursive anymore now in school, have you heard that? They're gonna, it's all to be printing, I guess, forever now. We're gonna stop teaching cursive. They say now. But anyway, yeah. So another thing that our buddy Gay-Lussac did was he realized that when you combine gases under the same conditions, in other words, the same temperature, the same pressure and such, they always combine in these little whole number ratios, like 1 to 2, or 1 to 3, or 2 to 4, or whatever. And so, for example, let's say you have hydrogen gas with chlorine gas combining to make hydrogen chloride gas. Well, if you were to measure out what volume of hydrogen gas do I need compared to what volume of chlorine gas do I need, it's going to be about a 1-to-1 ratio. So for every one whatever volume you're using, 1 milliliter, 1 liter, whatever, maybe it's 10 and 10, you're going to get out twice that amount of HCl. So if you use 10 of this, then you need 10 of this, and you get 2 of that. So it's about a 1-to-1 to 2 ratio. So that's pretty much ties in exactly with what we know about the moles, right? Because those ratios, 1 to 1 to 2, work for the moles, right? Yes?
Yeah.
For every 1 mole of hydrogen, I need 1 mole of chlorine, and I make 2 moles of HCl, right? You agree with me on that, right? Volumes work the exact same way. For every 1 liter of hydrogen, I need 1 liter of chlorine, and I make 2 liters of HCl. Or if it's 10 and 10, it's 20. It's the same thing. So these are small whole numbers, 1 to 1 to 2. Right. So he realized, yeah, it's the same kind of deal. So this is called the law of combining volume. Just the way they react in small volumes, or combine in small amounts of moles, they combine in small amounts with volumes, the exact same ratio. So it is exactly the same. So if you know the 1 to 1 to 2 is the mole ratio, then 1 to 1 to 2 is the volume ratio too. So that makes it much simpler then for us on these problems. We don't have to worry about so much about ideal gas law and masses and things like that, because if I know the volume of the hydrogen, I just know it's going to be the same volume of the chlorine. It's going to be a 1-to-1. Or if I know the volume of the hydrogen, I'm going to make twice that volume of the HCl. I don't have to worry about turning moles and 1 to 2 and all the other different things like that, because it is. It's the same thing. It works exactly the same way for volumes as it does for moles. Sure, just give you a quick example here. How many liters of oxygen would react with 37.5 liters of sulfur dioxide? So, basically, 37.5 liters SO2. Well, the same ratio that works for moles works for volumes. So just the way 2 moles of SO2 makes 1 mole of, needs 1 mole of O2, 2 liters of SO2 needs 1 liter of O2. Are you with me? So same thing. Just use that exact same mole to mole ratio, but now it's the volume to volume ratio. But it's the same coefficients there. So they're going to get half of that, right? So what's that? 18.8, yeah.
20, yeah.
So, nice. So that makes it very handy. So that's true again, as long as there's similar conditions. Now, if the conditions are changing, let's say it gets hotter as it goes through the products, or the volume changes or whatever, then all bets are off. But as long as it's it's closed system, keeps the same volume, keeps the same pressure, keeps the same temperature, then you can relate them with the same ratio. Okay, so this leads us to something called the molar volume. So the molar volume is a very handy thing. First I got to define a little term called STP. STP, Standard temperature and pressure. So in scientific circles, you often see things that things that are being reported at STP. Simple studied at STP. The results are at STP. So standard temperature and pressure are considered to be a temperature of 0 Celsius, which is 273.15 Kelvin, and the standard pressure is considered to be 1 atmosphere. So whenever you see things are at STP, that's what it means. 273 Kelvin, 1 atmosphere. Okay? Now, if you were to solve the ideal gas law, PV equals nRT, at these conditions, PV equals nRT, and you were to find out, okay, so what's the volume if I have N is 1 mole, temperature is 273, pressure is 1 atmosphere. If I were to plug all that in and find the volume, you would figure out it is 22.4 liters. Now notice I didn't say what gas it was, right? So it's kind of crazy to think about, but that means 1 mole of any gas at STP is 22.4 liters. 1 mole of any gas at 273 Kelvin and 1 atmosphere is 22.4 liters. So if you need to get yourself a mole of carbon dioxide, go get 22.4 liters of carbon dioxide. If you need a mole of oxygen, go get 22.4 liters of oxygen, 24 liters of hydrogen. Any gas, 1 mole of it is 22.4 liters when you're at STP at least, right? Of course, you're right. If the temperature was different, the pressure was different, it wouldn't be that. But that's called the molar volume. So 1 mole of any gas at STP is 22.4 liters. Yes.
So R, we just rounded the R.
Oh, yeah, just rounded on that one. Yeah, 8206, 821. Yeah, I don't know why I did that on that one. Okay, so let me make a little chart here. Let's go back to our friend the mole. So remember, we can go from moles to particles. And to do that, we used Avogadro's number, right? That's really messy. Try that again. 2 times 10 to the 23rd. We could go from moles to mass. How do we do that? Molar mass. Grams per mole. Now we can go from moles to volume of a gas. Because we know that 1 mole of any gas equals 22.4 liters. At least it does when you're at STP. So, I just added a new third leg to our little flow chart here, if you will. The next chapter we'll add a 4th one. But everything goes through moles. Moles is the crossroads. So I can now relate volume of gas to mass of a solid, volume of gas I can relate to atoms, ions, molecules, and vice versa. So we added a 3rd thing we can now connect, all going through the crossroads of the moles. So, but again, I'll say this is only true at STP, 0 Celsius, 1 atmosphere. Okay, if you're not at that conditions, you can't use that. And you got to do it the old-fashioned way with PV equals nRT and do all that stuff. Okay, well let's look at a couple of examples here with this. We'll wrap this chapter up here shortly. Okay, 1 mole of any gas. Again, that's only true at STP. So let's look one. What mass of calcium must react with phosphoric acid to release 37.85 milliliters of hydrogen gas at STP? So, when you see that at STP, You know, when you see the STP, you should be thinking, oh, now I can use molar volume because I'm at STP. So let's look at this. So 38.5 milliliters of this. What mass of this do I need to make that? So, what could I do? What do you think I can, how could I get from volume of hydrogen gas to mass of calcium? So I have to somehow turn volume of hydrogen gas and get that over to calcium. What could I do? Convert it into liters. Good start. Yes. So 1 milliliter is 10 to the negative third liters. Okay, now I have liters of hydrogen gas. How does that help me? What do we know is true at STP? 1 mole of any gas is what? 22.4 liters. So 1 mole of hydrogen must be 22.4 liters of hydrogen. So, let me back up. If I would have said, oh, I have mass of hydrogen, what do? You ought to win molar mass. But now I'm saying, oh, look, we have volume of hydrogen. What do? Molar volume. So, mass, you use molar mass. Volume, you use molar volume. Okay? Same deal. So now we're in moles of hydrogen. How do I connect that over to calcium? Mole to mole ratio, which is what is it? Between calcium and hydrogen? 3 to 3, right, exactly. So for every 3 moles of hydrogen, I need 3 moles of calcium. Right. I don't want moles of calcium, I want mass of calcium. Molar mass, yes, so calcium, 40.08, yeah, 40.08 grams is a mole of calcium. There you go. So let's try that in our calculators. Tell me what you get. Looks like 3 sig figs. .069, I don't know. Is that what it was? 0.069. Give me another one for 3 sig figs.
Oh, 0.689, sorry.
689. Really, you let me down. Okay, so I promise you, it's not much different. But now instead of using molar mass, we're just using molar volume for gases. Works the same kind of way. Okay. Problem to B. Your turn. Try B, and then we'll be done. Just that easy. So how many milliliters of hydrogen chloride gas will be produced from 25.0 grams of barium chloride at STP? It's not exact, no. It is 3 sig figs. But I had to calculate it out of that little equation I showed you, right? I set it up. I set V equals nRT over P, and I had to plug in all those numbers. Yeah. So it's not exact, no. You can find more sig figs you want to do. Here's some answers. How many milliliters of HCl? Oh,
5,080.
Is it like 5-3 something?
5,000 something they're saying. Okay.
3 times 7/3 milliliters.
Okay, I think you're making it too hard. If I had said what
Yeah,
mass of HCl, you'd have been all over it. You'd have done mass to mole to mole to mass.
5,000.
But I'm saying what volume? Mass to mole, but now mole to volume. So let's just look at it here. So what's the molar mass of barium chloride?
208.23.
208.23 is a mole of barium chloride. Okay, good. How do I relate barium chloride to HCl? Are you with me there? What do I do? Mole to mole ratio. For every 1 mole of barium chloride, 2 moles of HCl. Now let's imagine the problem said instead, what mass of HCl? What would you do? Molar mass, but it doesn't. It says what volume of HCl. So what do you do?
So 1 mole.
Molar volume, right? Yeah, 1 mole of HCl is 22.4 liters. I don't want liters, I want milliliters. Swear you're making it too hard. Negative third. Negative third. And what'd you get? Somebody give me an answer again?
5,380.
5,380. Or you could always do 5.38 times 10 to the third. I heard somebody say that too. That's fine also. Question? You see how we did that, Marilia? Okay.
I knew it, I just couldn't put it down.
Okay, yeah. So just like molar mass for mass, just start using molar volume for volume. If you're at STP. If you're not at STP, then you gotta do it the way I was showing you earlier, where you gotta use PV equals nRT, find the moles, plug it in, blah, 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 blah. Okay, well, we got 7 minutes left, so a few little reminders here. We are done with Chapter 7, so what's that mean? Homework and quiz on Monday on Chapter 7. So I just checked this morning, and probably over half the class hasn't done any Chapter 7 homework yet. Over half of the class. So you gotta practice this stuff regularly. So you're trying to cram it, trying to go back and remember, what was I doing? So I'm telling you, that's not working. So practice it regularly, and then you can ask questions regularly from me, the tutors, etc. So get on that homework. You got the rest of today, you got Thursday, you got Friday, you got Saturday, you got Sunday. So don't wait till Saturday or Sunday. Also, of course, science fair is coming up, right? So deadline is today to turn in your paperwork for the science fair if you are going to do it. I know one group turned it in today and found out theirs was already taken, so scramble and find a new one. And then I think it's next weekend, right? Next Saturday is that. I think it's the week from Saturday, is that right?
Yeah.
Yes, it's a week from Saturday, so like 10 days. Yeah, so I guess we'll see you Monday, if not sooner. So, work on that homework. Come back, ask me any questions you might have. Go to the tutors, ask questions.